let's finally begin the proof. We'll start with part one. So let's bring in some assumptions, and I've written this down in kind of a schematic way. We're assuming what I refer to as the good situation here, but a little bit more. We're assuming we have an algebra of sets on X and a non-negative countably additive function. So more than just what I had written back here in this summary last time, in the last video. Here I was just saying additive. We're assuming countably additive. All right. So remember, our first goal is to prove that A is a subset of A mu. So measurable sets are mu measurable. But look back here. When is A a subset of A mu? When this stuff happens. And this stuff is certainly happening in our case. We're in a situation where A is an algebra of sets. So, of course, it contains the empty set. And mu is additive, so of course mu over the empty set is 0. So we're going to use this, and one thing I thought might be fun is to put a little check mark next to a proposition when I use it or something, so that we fill this page with check marks and see what we end up having to use to prove the theorem. All right, so that's 1 for proposition 15L1, part 1. Since mu is additive, we have this first part of what we want. Okay, what's next? So we got this. Now we want to prove that mu star is an extension of mu. So, meaning if I start with something that's in the original algebra of sets, then mu and mu star will agree about what the measure of that thing should be. So, let A be something that's in the original algebra of sets. Then we want to prove that mu of A is the same as mu star of A. So I claim that one inequality is obvious, but I'm still going to say why, of course. So this inequality is clear. Why is that? Because this is the outer measure of A is defined to be the infimum of the approximations from above of A, right? This is the infimum of the approximations from above of A. And if you take, so what is an approximation from above? It's a countable family that covers A, and then you take the sum, and that's the sum of the mu's, and that's the approximation from above. So what if you just take this A by itself? That would be an at most countable family that covers A, right? And it's a family of sets in the algebra of sets. And then what would be the corresponding, what would be the approximation from above corresponding to this covering? It would be the sum of the mu's of everything in this set, but there's only one thing in this set. So just mu of A would be the only term in that sum. That is one of the approximations from above of A with respect to mu. So mu of A is one of the things in the set whose infimum is mu star of A, hence this inequality. All right, now we want to prove the other inequality. So how might we prove mu of A is less than or equal to mu star of A? Well, mu star of A is the infimum. It's the greatest lower bound of a certain set. What I can do is show that mu of A is a lower bound for that set. So we will show that mu of A is a lower bound for the set of approximations from above with respect to mu of A. So I guess we're really showing altogether here that mu of A itself is the minimum of the set of approximations from above of A. That's what we're really showing, since it's one of them, it's one of the approximations from above, and then we're showing that it's a lower bound. So the infimum here really ends up being a minimum. Okay, well, to show it's a lower bound, I should consider an arbitrary approximation from above. So consider any, and then how do I consider an arbitrary approximation from above? Remember, this was the definition. Approximations from above of B would be this collection of results of these sums, right? So I should consider an arbitrary countable family that covers my set A in my case, such that the series converges. So consider any sequence, let's call it AN, of sets in the algebra of sets, such that it covers, so the union contains A, and such that the series converges. The series of the mu's converges. So now my goal is to show that mu of A is less than or equal to the value of this series. The value of this series is what I'm referring to as an approximation from above, which would be an arbitrary element of this set. Now, here's a mistake that I almost just made. I wanted to say mu of A is less than or equal to mu of union ANs because I have this inclusion, and because I'm thinking about the monotone property, that whenever I have this inclusion I should get this inequality. But do you see why this is a mistake? I only know about fancy A that it's an algebra of sets, not necessarily a sigma algebra, so the union of all the ANs need not be an element of fancy A. So there might not be such a thing as mu of that. Okay, so the problem there is that this cover contains A as a subset. It doesn't equal A, but I can replace it by one that does. So we have, if I just intersect all of these with A, then that's the same. I can sort of pull out the intersection, right? You can view it like this. And that equals A, because it's A intersect something that contains A. So now I have this cover, and this equals A now. So let's see. Let me start with mu of A. Mu of A equals mu of this. No problem here. This union is A, which is an element of our algebra of sets. And then now I'm assuming mu is countably additive, right? That's one of the assumptions in our amazing extension theorem. We're assuming we're starting with something countably additive. So if these were disjoint sets, which I don't know that they are, but if they were, then I could say, oh, this equals the sum of the mu's. But one thing I do have from back here is that I have countable subadditivity. So this is an if and only if. It goes two ways. If I have countable additivity, which I do, I have countable subadditivity. So I'm now going to use this direction of proposition 139, part 3. So this is less than or equal to, this is subadditivity, the sum of these things. Oh, and by the way, these individual things are in the algebra of sets, since the A's and the AN, since A and the ANs are all in the algebra of sets. And an algebra of sets is closed under intersections, finite intersections. So nothing wrong with applying mu to this. Aha, but I just remembered a subtlety. With countable subadditivity, the way we defined it is that it applies in situations where the series converges. So we sort of have this inequality if the series on the right side of it converges. If the series on the right side doesn't converge, then you might say it equals infinity, in which case we also have the equality, but I just don't want to deal with that case. Okay, anyway, let me make some room here. This is bounded above by, so the terms of this, so the mu of A intersect ANs are always, for each n, this is going to be less than or equal to mu of AN, right? That's because of the monotonicity. So now I'm using this one, so let me give that a check mark. So then the terms of this series are bounded above by the terms of this series, but this series converges. So by the comparison test, this series converges. And by the order limit theorem also, what it converges to is bounded above by what this one converges to. And remember, these are non-negative series. These are series with non-negative terms. So that's why this works. And I think we achieved what we need here. So don't worry about the if the series converges part anymore, since it does, since it's bounded above by a series that converges. The terms are bounded above by the terms of a series that converges. And we have what we need. We have shown that mu of A is less than or equal to our arbitrary approximation from above. So from this, so we have shown that mu of A is a lower bound for the approximations from above. So thus, it's less than or equal to the greatest lower bound, which is the outer measure. Okay. So we have proven that mu of A equals mu star of A. We've proven both inequalities, and I think that's everything we needed for part 1. Yep, A mu contains the original algebra of sets, and the outer measure extends our original countably additive function. Okay, so that's part 1. Part 1 is actually fairly easy. Part 3 will be a little bit more complicated, and part 2 will be a lot of work. So we're still on the easy part of this.